Greetings, physics students. I wanted to take a few minutes and go over the 2D motion problems. We will be using the 5 equations of linear motion that we derived back in session 1. True, false. A change in velocity is always an acceleration. Acceleration is change in velocity over time, which you can write that way. So yes, whenever velocity changes, you have an acceleration. If the velocity decreases, then you would have a negative acceleration or a deceleration. If the velocity increases, you would have a positive acceleration. Now, where this gets interesting is where objects are not moving in a straight line. Remember, velocity is a vector quantity, and vector quantities give magnitude and direction. So if a car is going around a curve, its direction is constantly changing, even though its speed is not changing. So it's accelerating. Just a car simply going around a curve is accelerating, even if its speed stays constant, even if it's going 50 miles an hour the whole time. Just changing the direction gives rise to acceleration. And when we get to circular motion and gravity later on, if you think about a satellite, like for example the moon going around Earth, the moon or the satellite is constantly accelerating. Even though its speed is constant, around 2,000 miles an hour, it's still accelerating all the time because its direction is constantly changing. It's going in a circle. And this will become important when we get to Newton's second law, F equals ma, because if the moon is accelerating, that means there must be a force holding it in orbit, and of course we know that force to be gravity. True, false. In projectile motion problems, that's where we have a cannon, let's say, and it's shooting a cannonball, and it lands some distance down there. The horizontal and vertical components of an object's motion can be analyzed independently of each other. Actually, they have to be, they must be. The vertical component of its velocity, let's say, and the horizontal component of its velocity have to be analyzed independently. That's why we need to use trigonometry based on the firing angle to come up with the vertical and horizontal components of velocity. True, false. Ignoring air resistance. All these problems do. All these problems we're doing do ignore air resistance. Does a 45-degree firing angle, in other words, the cannon is pointed at a 45-degree angle right there, does that give a projectile its maximum range? So without going through a big derivation, that's the formula for range for a projectile motion problem, where theta is the firing angle. The range depends on the sine of 2 theta. Where does the sine function maximize out? What's the sine of a 0-degree angle? The sine of 0 is 0. You can use your calculator and check that if you don't believe me. What's the sine of 90 degrees? It's 1. 90 is where the sine function maximizes. If it was cosine, the cosine of 0 is 1. It's the other way around. Cosine would maximize at 0. But the sine function reaches a maximum value of 1 at 90 degrees. So if 2 theta has to equal 90 degrees, what is theta? If 2 times the firing angle is 90, what does that mean theta has to be? That's how you would answer this question. This is a classic sort of problem. The way it's usually set up is you're taking a boat across a river, and the river is flowing sideways to your direction of travel, or you're flying an airplane and there's a crosswind blowing. So in this case, the river is flowing at 2 meters per second, north to south, and you're taking a boat straight across at 4.2 meters per second. So intuitively you know, let's say you start here and you head this direction, you think, you're pointing that direction, but your actual travel is going to look like this, and you're going to land on the opposite bank some distance downstream. Part A, how much time is required for you to cross the river? You're given the width of the river, 800 meters. You know you're going 4.2 meters per second due east, and it's asking for time. So you have time, velocity, and distance. So that equation looks like this. We could substitute d in for delta x. So how do you arrange this equation to solve for t? Simple algebra. You would multiply both sides of the equation by t, and you would divide both sides of the equation by v to give you this. And then substitute d in there. We're given that in the problem as 800 meters. Substitute the velocity in there. We're given that as 4.2 meters per second. And since we end up with units of second in the denominator of the denominator, like this, the seconds ends up on top, and we end up with the units that we need. And you'll end up with an answer in this range. Now you're asking, why didn't we take this velocity that's angled slightly southward in order to come up with the time? The reason we didn't is because we're given the distance straight across, east to west, as 800 meters. We're not given this distance going at an angle. We could use this velocity here if we had this distance here, but we don't. So since we're given the distance straight across, and the problem says we're moving 4.2 meters per second due east, that's the key there, we can use that velocity and that distance to solve for the time. Part B, how far south of your starting point will you be? So now it's asking, what is this distance? How far downstream have you drifted? Write the equation for velocity. Rearrange for distance. In other words, multiply both sides of that by t. In this case, you know the time that you are in the water. You just solved for that. I told you it was between 150 and 200 seconds. It's just 800 divided by 4.2. And the velocity that you use has to be the velocity going from north to south now, right there, which was stated in the problem. So this is a very simple multiplication problem. It's just 2.0 times the time that you solved for over there. And as a self-check, your answer should be in the range of 350 to 400 meters. This is a very typical projectile motion sort of problem. The first thing you need to do is convert 50 yards and 150 yards into feet, because the problem is dealing in feet per second. So how many feet are in a yard? We want the feet on top, the yards on the bottom, so that the yards will cancel out and we're left with feet in the numerator. So that's 150 feet. This one, the same thing. We want to put the feet on top, yards on bottom. So this is 450 feet out here. The problem is asking how far the bullet drops with two different targets, one close and one far away. So we need to know how long the bullet is in the air in both cases, so we can then calculate as a free fall problem how far the bullet drops. The basic equation looks like this. Velocity is distance over time, delta x over t. I'm just substituting d in for delta x. And we want to rearrange to solve for time. So we need to do an algebraic rearrangement. How do you isolate time on one side of the equation? You'll need to multiply both sides by t and divide both sides by v. So for the near target, it's 150 feet in the numerator, 750 feet per second in the denominator. The feet cross out, we're left with seconds, in the denominator of the denominator, so the seconds will come up in the numerator, which is what we want. For the distant target, we would use 450 over 750 feet per second to get the time down here. So the time the bullet is in the air is just a tiny fraction of a second. That one's 0.2 second. This one I'll let you calculate. It's 450 over 750. So step back. What have we just done? By isolating the x direction from the y direction, we've determined that the flight time of the bullet in both cases. We haven't even considered the y-axis yet. We've just simply looked at the x-axis. Now, step 2, in order to figure out how far the bullet drops during flight, we have to flip the problem sideways and look at the y-axis in isolation. We have to talk about the y-axis and ignore the x-axis, in other words. So it becomes a free fall problem. Initial velocity is 0, so we can analyze the problem as if you just dropped the bullet straight down and let gravity pull it down. The initial velocity would be 0, and the time that it's in the air, the hang time, for the near target anyway, is 0.2 second. So if you look at the 5 equations of linear motion, that's the one you want to use right there, because we can solve for the distance. The initial velocity is 0, so that term's going to cross out. We know the acceleration due to gravity, it's just g, or 32 feet per second squared, and we know the time that it's falling. So I'm going to rewrite the equation using delta y because we're dealing in the y direction, the up and down direction. This term goes away because initial velocity in the y direction there is 0. 1/2 a, or the acceleration due to gravity in US units, looks like this. Your books may or may not have this, but the acceleration due to gravity in the metric system is 9.81 meters per second squared. In the US units, we use 32 feet per second squared. In the time we just solved for up above, so that looks like that. Remember to square the time. And so for the near target, the bullet falls not quite a foot, 0.64 feet, on its way to the target. Now for the far target, of course, it's going to fall a lot further, but you use the same equation, and for the time, you use the value that you calculated right here. And again, don't forget to square the time term there. And to give you kind of a self-check, it's between 5 and 6 feet. It falls a long ways, in other words. Now, you're flying an airplane. The airplane is moving at 165 kilometers per hour. You open the door and push out a 100-kilogram crate. And the parachute apparently was from the low bidder because it says it fails to open, and the crate crashes 4.5 seconds later. So you analyze part A like a free fall problem. You know the hang time here, and you know the initial velocity of the crate. What are you doing? You're separating the y-axis from the x-axis. You're not even considering the crate's horizontal side-to-side movement. You're just analyzing the up and down movement separately, and that's what you have to do with these types of problems. So you probably want to use this equation right here to solve the problem. It's asking for the final velocity. You know the initial velocity is 0. You know the acceleration is going to be the acceleration due to gravity. And you know the hang time. Substitute 0 for the initial velocity. Since we're dealing in the metric system, use 9.8 meters per second squared for the acceleration due to gravity, and you're given the time in the problem as 4.5. So the final velocity is 9.8 times 4.5. Part B, how high was the plane when the container was released? In other words, you know the hang time was 4.5 seconds. So analyze this again as a free fall problem like this, where you know the final velocity now, which you just calculated in part A. Looking at your choices, I would choose that one, because you can solve for the distance, i.e. the height of the plane, and you know all the information given in this formula. So again, I've written it as delta y because we're dealing in the y-axis. Velocity 1 is 0, so that whole term zeroes out. And so the distance, the delta y, the height of the plane at the time you push the crate out the window, is just 1/2 times 9.8 times the time squared. Make sure you square the time term. And as a self-check, your answer should be between 75 to 150, and we're working in meters here. Part C, did the crate end up in the lake? Apparently, there was a lake 1/2 kilometer west of the plane when you pushed it out the door. So for this, we're switching back to the x-axis now, and we're ignoring the y-axis. You know the x component of the crate's velocity, it's given right here, 165 kilometers per hour, and we're ignoring wind resistance. So the x component of the crate's velocity all the way down to the ground, or to the lake, is going to remain at 165 kilometers per hour. And you know how long the crate was traveling through the air, 4.5 seconds. So you have all the information you need. We're going to need to use velocity equals distance over time, and then rearrange that to solve for distance. So to do that, you would just multiply both sides of that by t, like that. The velocity is this. We're going to need to convert that hours into seconds. How do you do that? Well, you know there's 60 seconds in a minute and 60 minutes in an hour. So you can save yourself some time. 60 times 60 is 3,600. So the conversion factor needs to have hours on top and seconds on bottom. You know that because we want the hours to cancel out. So there's 3,600 in the denominator and a 1 in the numerator. And then the time right there is stated in the problem, 4.5 seconds. And so your distance is just 165 divided by 3,600 times 4.5. And so get that distance in kilometers and compare it with this information right here. In other words, there's a lake down here, a red lake, 0.5 kilometers from where you drop the package. There's the drop. So that distance apparently is 0.5 kilometers. And you just solve the distance that the crate actually traveled. Is that more or less than 0.5 kilometers, in other words? And so this is a really good problem which illustrates how we isolate the y component from the x component in solving complex problems like this. Here we have a diver. What horizontal velocity will he need in order to miss this ledge, which apparently sticks out 1.75 meters at the bottom, given the fact that the cliff is 9 meters high? So the strategy for this problem is to calculate how long he's going to be in the air before he hits the ledge. The vertical component of his motion is entirely independent of the horizontal component. So we just analyze the vertical component using the acceleration of gravity and the fact that the cliff is a certain height. and you can find out his hang time before he splats on the ledge. Knowing that, you can then calculate what horizontal velocity, v0 here, he would need in order to just barely clear the ledge. First part of the problem is going to look like this. I would use this equation of motion, again plugging in delta y instead of delta x. It's made a little easier because v1 is 0, so that term will drop out. So it really looks like this, and we need to isolate it for t, so you need to do a bit of algebra. Step 1 would be to divide both sides by a. Step 2 would be to take the square root of both sides. And if I did that correctly, you should get that. So substituting values, you get this. So it's just 9 divided by 9.8. And you see what happens in here. The second squared comes up on top. And since we're taking the square root of that, the units out here just end up being seconds. And so it's 9 over 9.8. So it's just under 1. I'm getting about 0.96 seconds there. So now that we know that, we need to flip the problem sideways and focus on the x-axis now and ignore the y-axis. We know the hang time is a little less than 1 second. So the picture looks like this. We know he has to clear 1.75 meters because that's the size of the ledge, and he has to do it in 0.96 seconds. So we use this equation for velocity, distance over time. So we're just plugging in values. The distance is 1.75. The time is given, and that will give you the necessary horizontal velocity, his horizontal speed that he has to leave the edge of the cliff in order to miss the ledge. And just as a self-check, the answer I'm coming up with is between 1.75 and 2 meters per second in the x direction. So here you're on an unknown planet and you're trying to figure out the local value of g. What is the acceleration of gravity on that planet? So a crew member kicks a stone at a 45-degree angle from the ground at a speed of 17.6 meters per second, which some way you're able to measure, and the stone lands 33.8 meters away. Step 1, develop a strategy to attack the problem. You know the angle and you know the speed, so you could, using some very simple trigonometry, calculate the y and x component of that velocity, of that 17.6 meters per second. Once you did that, for example, knowing the x component and knowing the distance, you could then calculate how long the stone was in the air, what is the flight time, in other words. And then once you know the flight time, you could set up, in essence, a freefall type problem in the vertical direction and calculate the acceleration from that. So draw yourself a neat triangle showing a 45-degree angle and with the hypotenuse equal to 17.6, and then write down SO, CA, TOA. That stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And ask yourself which one of those three functions, sine, cosine, or tangent, is going to help you. Well, you're trying to solve for Vx down here, and you know the hypotenuse. So the cosine function is what you want to use here. And you would write it like this. Cosine of 45 degrees is adjacent over hypotenuse. So standing here at the 45-degree angle, your adjacent side is right here, Vx, the velocity in the x direction. And the hypotenuse, of course, is the 17.6. And rearrange so you can solve for v sub x. So v sub x is just 17.6 times the cosine of 45. Get your calculator, type in 45, hit the cosine button, and then go times 17.6. And the answer there is 12.4. The units are meters per second because you just solved for the x component of that stone's velocity, 12.4 meters per second. So in other words, the person kicks it at 17.6 meters per second at an angle. The x component of that represents 12.4 meters per second. Now the y component is going to be the same because it's a 45-degree angle. And if you take the sine of 45, you're going to get the same answer. So the Vy is the same in this case. It's kind of a simplified example. If the angle was not 45, if it was 30 degrees, then no, Vy wouldn't be 12.4. It would be a different number. So what have we just done? We've solved for the horizontal velocity, in essence, 12.4 meters per second, and we know the distance, and we want to calculate the time. So we just use this equation here and rearrange it for time and solve for time. You rearrange this to solve for t, as shown here. Basically, again, you're multiplying both sides by t and dividing both sides by v. You plug in the distance here, and you plug in the velocity, 12.4 there, and you get time. You'll get an answer between 2 and 3 seconds. So it's airborne for that number. So step back, what have we just done? By isolating the x-axis and ignoring the y-axis, we have just solved for its flight time. There's no other way you could do that. If you look at this arc, and you know its speed at that angle, there's no way you can solve its flight time unless you isolate the x-axis first. Now we move on to the next step. We've calculated part B, how long was the stone in the air, right here. Now we're going to focus on the y-axis and we're going to ignore the x-axis. Here's what the picture looks like. It would start on its upward journey with a velocity here. I'm using a negative sign, 12.4 meters per second. Eventually it's going to slow down and stop. It's going to have a velocity of 0, and then it's going to turn around and do the exact same thing on its way down, starting with a velocity of 0 and ending just before impact with the same velocity that it started with, plus, this time positive, 12.4 meters per second. Now, we could look at both halves, the trip upward and the trip downward, as taking place in 2.7 seconds, or we could just make this easier and divide 2.7 in half and just look at its upward journey. Half of 2.7 is 1.35 seconds. So the time it would take going up, 1.35 seconds. The time that it takes going down, 1.35 seconds. And we can just ignore the trip down, focus on the trip up. And so looking at your choices, this is probably the best choice right here. So looking at the formula, V2 here is going to zero out. V1 we know, time we know, acceleration we're trying to solve for. So it's probably easiest to rearrange the formula first before we plug in values. So bring the V1 over on this side and call it negative V1, and that would leave that. We're trying to solve for acceleration, so we want to move everything else on the other side of the equation, in other words. So substituting would look like this. V1 is a negative number, negative 12.4, but there's a minus sign out here. So the numerator is going to end up being positive. So as a self-check, the acceleration ends up being between somewhere between 9 and 10 meters per second squared, which is the answer to part A. Okay, and then lastly, how high above the ground does the stone go? You have two choices really, this one and this one. They both have a delta x term in them. But since this one is already expressed in terms of delta x, I would go with that one. For V1, you would use 12.4 meters per second, but it has to be negative. We're counting upward velocity as negative. time is 1.35 seconds. The acceleration you just solved for, and then again time, and make sure you remember to square the time term. And you'll end up with a negative number. The way we have the signage working here, you'll end up with a number between 8 and 10 meters, but it'll be negative. All that means is the way we have the sign convention worked out, it ends up being a negative number, but it represents the height that the rock goes, which is the answer to part 3. Okay, if you have any questions about this homework, just let me know.